All right. Our next section on probability is called conditional probability and the multiplication rule. Again, some definitions to start with. A conditional probability is the probability of an event occurring given that another event has already occurred. The conditional probability of an event occurring given that the event A has occurred is denoted by, here's going to be your notation, and we read that probability of B given A. So the probability of B given that A has already occurred. So, example 1. 2 cards are selected in sequence from a standard deck. Find the probability that the second card is a queen given that the first card is a king, and assume that the king was not replaced. So before we do that, let's do just a real quick side note on cards in case you don't know. So your sample space includes 52 cards. There are 52 cards in a deck. There are cards that look like an ace, or sometimes a 1. There's a king, there's a queen, and there's a jack. These are often called face cards. Oops, not all of them, sorry. Sometimes the ace is the highest card, sometimes ace is the lowest card in the deck. That's why sometimes people refer to it as a 1. These 3, the king, the queen, and the jack, are called face cards. And then we have additional number cards. We have a 10, a 9, an 8, 7, a 6, a 5, 4, 3, 2. Like I say, the 1, some people refer to as the 1 or the ace. Typically, the ace is considered the high card, but it can also be, depending on the game you're playing, be a value of 1. So that's why it's sometimes the 1. Okay. We also have 4 suits. There are 2 red. There are 2 red suits, which are the diamonds and hearts. There are 2 black suits, which are clubs and spades. So it's very important that you know what's in your sample space. So there are then 13 of each suit. So there are 13 of each suit. So there are 13 diamonds, 13 hearts, 13 clubs, 13 spades. And if you add these up, there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you would have a 2 of hearts, a 2 of diamonds, a 2 of clubs, and a 2 of spades. And likewise for each one of those. So there's 13 of each suit, 52 total cards. So this one says, find the probability that a second card is a queen given that the first card is a king. So that's the probability that you get a queen given that the first card is a king. The probability that you have a queen given the first card is a king. So if the first card is a king and it's not replaced, my sample size then decreases by 1 and is only at 51. Because the king was chosen, I only have 51 cards left. So the probability that I get a queen, well, there are 4 queens that are possible, none of which have been chosen yet. All we know is 1 king has been taken out of the deck, basically. It's already occurred. So the probability now that I'm going to get a queen to follow that would be there's 4 queens. 4 out of 51 would be approximately 0.078. So about 8% of the time you would get a queen following a king that's already occurred. So not all that often. It is important that you know how to use the cards in the deck. All right, number 2. The table below shows the results of a survey for 2,276 social media users that were asked whether they have been offended by something they saw on social media. On the probability that a user was male, given that the user was offended. So we want the probability that we have a male, given that the user was offended. So we know, basically what this is saying is we know that the person that was chosen was offended. We already know that occurred. So what's the chances then that they are male? So this is going to be the probability that we have a male, given that they were offended. So yes, offended. So probability that we chose a male. Well, that's going to come from this column. The probability that we chose a male, given that they are offended, here's the yes. So there were 1,151 offended people, of which 532 were male. So 532 divided by 1151, which is approximately 0.462. So let's do another one real quick. What's the probability that it is female, given that they were offended? So same grouping, same category, same part of the chart we're looking, only this time we want the females that were offended. So that would be 619 divided by 1151, which is approximately 0.538, which makes these two complements of each other. Complements, opposites. We'll do one more. What is the probability that, actually let's do 2 more. What's the probability that they are offended? This is not an A given B problem. This is just the fact that they're offended, because you could have a table that looks like this. So what's the probability that they were offended? Well, there would be 1,151 offended people out of the 2,276 that were surveyed. So this time we have to get to the total on this column. So 1151 divided by that is approximately 0.506. So about 50% of the people are offended. And then one last one. What's the probability that they said that they were offended? So yes, offended, given that it was a female. So it's worded a little bit different. It's worded a little bit different than this one. This one is the probability that they're female, given that they were offended. This one says, what's the probability that they were offended, given that they're female? So this time, I have to look at the total number of females that were surveyed. So the total number of females this time is 1168. because I chose a female. So that's going to be my denominator. And then my numerator is going to be how many offended females were there. So there were 619 offended females, which is approximately 0.5. So it's all in reading the problem and deciphering which pieces you're going to pick off that chart. But certainly the mathematics is not hard. Practice is what's going to make this simpler so that you can read and see what they're really asking. All right, next we talk about independent and dependent variables. Two events are independent when the occurrence of one of the events does not affect the probability of the other event. Events A and B are independent when the probability of B given A is equal to the probability of B alone. So B given A is equal to just the probability of B. It doesn't affect the others. When the probability of A given B is also just the probability of A. So depending on how you word these, the given part, the first one, probability of B does not depend on A. Probability here of A does not depend on B. Much like I reversed these two problems. This was female, and they were offended, given they were offended. This is what they've offended, given that they were female. So it's the same given problem, same conditional problem, only backwards or reversed, which is not uncommon to see. Events, obviously, then, that are not independent would be called dependent. So if one depends on the other, then they would be dependent. Not sure why it's flipping so much. All right, so classifying them as independent or dependent. Selecting a king from a standard deck of 52 playing cards, not replacing it, and then selecting a queen from the deck. So selecting a king, and then selecting, not replacing it, and then selecting a queen. So we can do this mathematically, which is nice. So the probability of B is equal to, and that's the probability of a queen. There are 4 queens in the standard deck of 52 cards. So P, probability of a queen, is 4 out of 52. The probability of picking a queen, given that a king has already occurred, we already determined that, is the probability of a queen, given that a king has already occurred, and we determined that that was 4 out of 51. Because now we took that king out of the deck. So there's only 4 queens left out of 51 cards. Okay. Since the probability of B is not equal to the probability of B given A, these events are dependent. They are dependent. One depends on the other. The queen depends on the king, in other words. All right, tossing a coin and getting a heads, then rolling a 6-sided dice and obtaining a 6. So again, the probability of B, which is equal to the probability of rolling a 6. Well, there's only 1 6 on that die, so it's 1/6. The probability of B given A is equal to, well, this says the probability of getting a 6 given that you already have a heads. Well, whether you get heads or tails doesn't matter about the 6. So the probability that you're still going to roll a 6 is still 1 out of 6. Doesn't matter what you got on the coin. So the coin and the die are not related. So that's going to make these two independent. mathematically wise, it's because the probability of B is the same as the probability of B given A. Sometimes you don't have to do it mathematically. Sometimes you can just look at the problem and say, all right, are the dice and the coin related? So in this case, the die and the coin don't relate each other. They're not impacted on each other. So they have no impact on the outcome. Right. Now this next one is going to be a little bit, perhaps a little bit thoughtful. So driving 85 miles per hour is the A event, and getting in a car accident is the B event. So the probability of B given A. Well, I don't have any numbers to plug in here. But do you think that getting in a car accident depends on your speed? Because that's what this is saying. Does the car accident depend on speed? Well, I can't necessarily say yes or no, but I can say that in all probability, the faster you go, the more likely you are to get into a wreck. So it is very possible then that speed does depend on that car accident. So these two would be dependent. Now, again, it's not always the case that speed causes a car accident. That's not what we're saying here. But we are saying that it is possible that speed can cause a car accident. Not always, but certainly a factor. All right. Next one is called the multiplication rule. The multiplication rule says the probability that two events A and B occur in sequence is probability of A and B equals the probability of A times the probability of B given that A has already occurred. If the two events are independent, that's why we needed to know whether they're dependent or independent, then the rule can be simplified to probability of A and B just to the probability of A times the probability of B. So we'll explain this a little bit more. But basically, we're looking at whether they're dependent or independent, and we're going to be multiplying these together. So it works out okay. Two cards are selected without replacing the first card from a standard deck of 52 playing cards. Find the probability of selecting a king and then selecting a queen. So we are not replacing the first card. So what's the probability that we get a king and then a queen? A king and then a queen. Right? So this would be the probability of a king times the probability of a king given, backwards. We chose the king first. So the probability of getting a king and then the probability of getting a queen given that the king was already chosen. So the probability of a king would be 4 out of 52. The probability then that I get a queen would be 4 out of 51, because again, we took that king out. If I multiply those together, I get approximately 0.006. I also like to think of this in a slot problem, because sometimes that makes this sort of make sense to you for a little while. So I have two choices here. The first choice is that I get a king. So probability of getting a king. Well, I have 4 kings out of 52 cards. Then I don't replace the card. So instead of having 52 cards, I now have only 51 cards. The probability of getting a queen is now 4. So it's the same formula as it is here, meaning my answer is still the same. But the way I thought about it might be a little different. This way, of course, is using more formulas, which is fine. This way is using a little bit more, maybe, I don't want to say logic, but a little bit more thing that may make sense to some of you. And that's fine. As long as it makes sense in your mind, you should be okay. All right, a coin is tossed, a die is rolled. What's the probability of tossing a head and then rolling a 6? So the probability that we get a head and 6. Again, because we already know these are independent events. One does not depend on the other. This would just be the probability of a head times the probability of a 6. So heads would be 1/2. 6 is 1 out of 6. So together I would have 1/12, which again is approximately 0.083. Probability of heads and a 6. And again, you could look at these as slot problems. Here's the head, here's that. So let's try some additional problems. An anterior cruciate ligament, or ACL, reconstructive surgery. For that surgery, the probability that the surgery is successful is about 95%, or 0.95. Find the probability that 3 ACL surgeries are successful. Okay. So this is the probability of a success on the first one, a success on the second one, and a success on the third one. Dependent or independent events? Well, every person is different. Every surgery is a little bit different. The damage may be a little bit different. So they certainly are not depending on each other. One person's success does not depend on another person's. So this would just be 0.95 times 0.95 times 0.95. Multiply those together, and we get approximately 0.85. I'm not using the calculator for these. I've already done out the mathematics to them, but certainly you can double check the mathematics. Find the probability that none of the surgeries are successful. So that's going to be the probability of no success, and then another non-successful, and then another non-successful. So what's the probability of no success? Well, if the probability of a success is 0.95, then no success would be 1 minus 0.95, which is 0.05. So this would be 0.05 times 0.05 times 0.05. When you multiply that together, it would be 0.0001. So rarely would you have 3 non-successful surgeries. It's possible, but it's rare. Now comes the words we have to really think about what the words say. Find the probability that at least one is successful. Well, at least one then would say that not all are unsuccessful. So at least one successful says not all are unsuccessful. Not all are unsuccessful. So that would be the probability of at least one success is 1 minus the probability of no success, which is equal to 1 minus 0.0001, which is equal to 0.9. So the probability that at least one of them is successful out of the 3 is very high. All right. Again, some more examples of using the multiplication rule. In a recent study, 18,187 medical school seniors applied for residency programs and submitted their program choice. Of these seniors, 10,050 were matched with residency positions, with 79.2 getting one of their top 3 choices. Medical students ranked the residency programs in the order of preference, and the program directors rank the students. The term match refers to the process where they are matched with the student's preference and the program director's preference. So, all that to ask the question. Find the probability that a randomly selected senior was matched. So a randomly selected senior was matched with a residency position, and it was one of their top 3 choices. So probability of A, which is a matched residency, let's just write it this in here. Is equal to 17,057 divided by the total number of seniors or people, medical students, is 18,187. So that's going to be approximately 0.938. Because this is an AND, I also need the probability of B given A. And the probability then that they had top 3 given that they matched their residency. And so if we read the question here, it tells us, of these seniors, those who matched the residency positions had about a 79.2% chance of getting their top 3 choices. So the probability that they got a top 3, given that they were matched, was 0.792. That makes these 2 events dependent, because one depends on the other. And now we have the probability of A and B equal to the probability of A times the probability of B given A, which is equal to 0.938 times 0.792, which is approximately 0.743. Some of these can be a little trickier in the way they're worded, so you just have to be very careful. Number 2 says, what is the probability that a randomly selected senior who was matched to a resident position did not get matched to one of their top 3 choices? So in terminology, this would be the probability of not being a top 3 choice given that their residency was a match. So this is the probability of not 3 choices, 3 top, given that they did match their residency. This is not an and statement. This is just asking that question. So if we know what this one B given A is 0.792, then this would be 1 minus 0.792, since they are complements of each other, which would be 0.208 approximately. And then number 3, would it be unusual for a randomly selected senior to be matched with a residency position and that it was one of the student's top 3 choices? Well, the answer to that we already discovered was 0.743. 0.743. So that tells you how likely it is to happen. It's likely to occur 0.743. So that tells us then it is not very unusual. So it is not unusual. So it is likely to occur. You can also look at this in mathematical terms, because 0.743 is greater than the 0.05. This 0.05 comes from the empirical rule. If you remember back from the last chapter. The empirical rule, again, going back to your bell curve, remembering that 68% are in this first, 95 in the second, 95%. And so since this is way in this group, then it is not an outlier. It is definitely in this group right here. A little bit more than the 68, but it's definitely in this group. So it's not an outlier. The outliers would be the green pieces, which is this. Since it's not an outlier, then it would be very usual and likely to occur. All right, and that wraps up our next section.